Okay, so what else can we measure? Well, we can measure temperature. And so you are familiar with, of course, you grew up in the United States, and you are familiar with the Fahrenheit scale here depicted on the left. You know that 98.6 degrees is normal body temperature, and that water boils at 212, and it freezes at 32. And if it's 45 degrees out there, you know, it's a pretty chilly day. Whereas I grew up in Germany, and if it was 45 degrees out there, it was freakishly hot, because 45 degrees, if you look, it's going to be above 100 Fahrenheit, of course. But scientists work, of course, for the most part, they report their temperatures and measure temperatures in Celsius. But a lot of the formulas that you will be using use the Kelvin scale. Now, the good news about the Kelvin scale is that the increments are the same, that 1 degree Celsius is the same magnitude as 1 degree Kelvin, and so it's easy to convert it. All you have to do is you have to add 273 to Celsius in order to derive degrees Kelvin. They simply took the freezing point of water, made it 0 degrees, and the boiling point of water, made it 100, and then divided it into 100 increments, and one of those increments is a degree. Okay, so we or you will be required to convert between the either Kelvin to Celsius or Celsius to Fahrenheit, or both, and you should be familiar with these formulas down here, right? So here's the temperature in Kelvin. You just plug it into this formula. Of course, this is just canceling the units. So your formula will simply simplify. How about that? So Kelvin is just, as I said earlier on the slide, 273.5 plus whatever your degree Celsius is. So if you have 100 degrees Celsius, you plug that in, it's 373.15 degrees. And if you go the other way, then you take, which is what this is here, you take the temperature in Kelvin, you subtract 273 from it. Going from Celsius to Fahrenheit, or Fahrenheit to Celsius, is a little bit more complicated. We have this fraction here, 9/5, which is 1.8. So this formula here, going from Celsius to Fahrenheit. So Fahrenheit, 9 divided by 5 is exactly 1.8 times degrees Celsius, and then you have to add 32. And the other way, you actually can take this formula and rearrange it, and so, but then you have, so you don't follow the order of operations here. You have to take the temperature in Fahrenheit and subtract 32 before you apply the 1.8, or in this case it's 1 divided by 1.8, or 5/9. Let's just, you have access to these, let's just practice a couple, go from there, it'll be good. So if I'm converting 37 degrees Celsius to Kelvin, all I have to do is take 273.5 degrees and add it to 37 degrees, which equals 310 Kelvin. And I put the decimal there because we have 3 significant figures. This is an addition, and we can go out to the nearest degree. So the answer is 310 degrees Kelvin. So this is the formula that you use. If you're going from Kelvin to Celsius, you just rearrange this, right? You subtract Kelvin from Celsius. So here we're going from Kelvin to Celsius. So it's 120 minus 273, which is equal to negative 153 degrees Celsius. If I also wanted to convert Celsius to Fahrenheit, I would use this formula here, right? So I would take minus 153 degrees Celsius, multiply it by 1.8 first, and then add 32 degrees to it, and I get negative 243 degrees Fahrenheit. Okay, so that's pretty cold. So that's this formula here. So you take, again, it's 37.0 degrees Celsius times 1.8, and since this is exact, I still get 3 significant figures, and the 32 is exact, so I can have 1 behind the decimal. So this is going to be very close to body temperature, 98.6 degrees Fahrenheit. Going from Fahrenheit to Celsius, you can rearrange the formula, the 5/9, and just divide by 1.8. And of course you have to first subtract Fahrenheit from 32. So we have 375 minus 32 divided by 1.8, and you have 190.6 Fahrenheit. And in this case we have 3 significant figures, and so we have to say 191 degrees Fahrenheit. Okay, so that's temperature. Moving on to volume. The SI units are is actually meters cubed, right? We measure volumes in height times length times width, and therefore the liter is actually a derived unit, right? So this is a derived unit because it uses some of the basic units. Anyway, if you have pure water, and 1 milliliter of pure water is actually 1 cubic centimeter, and that's because its density, and we'll talk about density in a minute, is 1 gram per milliliter. So what we have is just as shown here. If we have, and the volume of anything that is 1 centimeter by 1 centimeter by 1 centimeter is 1 milliliter, or 1 cubic centimeter here, right? So 1 cubic centimeter is equal to 1 milliliter. And a liter has 1,000 milliliters, if you remember that, or maybe I haven't mentioned that yet, but there's 1,000 in there. So if you have a 10 by 10 by 10 cube, it's 10 times 10 times 10 is 1,000, then you have 1,000 cubic centimeters, or 1,000 milliliters, which is also equal to 1 liter. Okay, and if you remember the deci, there are 10 centimeters in 1 decimeter, so this distance here is also 1 decimeter. Okay, and so therefore 1 decimeter cubed is equal to 1 liter. Now let's say we were to convert 1 meter cubed, right? So 1 meter cubed to liters. Okay, or let's do milliliters. It's more fun. Okay, so that gets a little tricky here, right? But you can use the metric system to get there. You know that 1 milliliter is equal to 1 cubic centimeter. So what you can do is you can go, you know the conversion between meters and cubic centimeters, right? So you know that 1 centimeter equals 10 to the minus 2 meters. And so what you can do is you can take 1 meter cubed and you can convert that to centimeters. Okay, now be careful here, right? Because we know that go away, that 10 to the whoa, that was weird, 10 to the minus 2 meters equals 1 centimeters, right? So that's great, but the problem is that this is cubed, right? So this, if you divided that and just did it the way it is, the meter would go away, but only one of these meters would go away, so it would still be meter cubed. And so we actually, in order to do this properly, you have to cube this entire conversion factor here, right? So this conversion factor then turns into 1 centimeter cubed equals 10 to the minus 6 meters cubed, right? So we had to cube this, 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 and this. So now we can do this. 1 meter cubed times 1 centimeter cubed divided by 10 to the minus 6 meters cubed, and then of course 1 milliliter is equal to 1 cubic centimeter. What you get is 1 times 10 to the 6 milliliters. So 1 meter cubed has 1 million milliliters in it. Okay, so you gotta always watch out for those units, right? Make a simpler problem here. What is the volume of a box below? You have length, width, and height, and so all you have to do is take the 24.2 centimeters times 20.8 centimeters times 12.5 centimeters. You multiply those three numbers, you get 6,290, and centimeter times centimeter times centimeter equals centimeters cubed. We have three significant figures here. So if I wanted to be report this in scientific notation, it would be 6.29 times 10 to the 3 centimeters cubed. That is the volume of that box. Okay. Density, that is also a derived unit, and what is good about density is it's an intrinsic property of matter. Okay, matter is everything that stuff is made up of, and chemistry studies matter and its changes that it undergoes. And so if you have a kilogram of water or a milliliter of water or 10,000 gallons of water, the density, the mass to volume ratio always remains the same. So it's independent of quantity. And it turns out that water has a density of 1.0000000 grams per milliliters. Okay? And that is also why we know that 1 milliliter is equal to 1 cubic centimeter of water. Okay? So you can convert milliliters to grams very easily if it is water. Then things or matter that is more dense, if you have a rock that is more dense, obviously, or a metal, it's going to sink in water. And if you have something like wood that's less dense, it's going to have a density that's less than 1.0, and it will float. And that's the concept. And so if you, as shown here, you have some sort of spongy looking or rock or material that's less dense than water, and it will float on water, just like oil floats on water. And then I have a granite rock or something that's more dense, and it will sink. It has nothing to do with weight. If you have a 1 ton log of wood, it's still going to float on water. It has nothing to do with how much there is. It just has something to do with the mass over volume ratio. Okay, and so we can determine the density of matter, which is one of the labs is that, and after this lecture you are ready to do this lab, and I encourage you to do both the first and the second lab right away as soon as possible, so you can practice measuring, converting, and how to determine density. Alright, so if we have a regularly shaped object that has a defined length, width, and height, we can just measure it right multiply the C to get the 3 to get the volume, and then we put it on a scale and we divide the 2. If we have a liquid, we can measure, and this is bad because these guys went above the scale, 25 here, but it doesn't matter. So what you do is you can weigh this graduated cylinder empty and then pour an amount of liquid that you're trying to determine its density of into there, and it doesn't matter whether you go to 15 or 20 or 25 or 14.7 milliliters, right? And then you weigh it after and you get the mass to volume ratio, right? So it's an intrinsic property that doesn't matter how much quantity, as long as you're able to get a volume and a mass, and you can divide the 2. If you have an irregularly shaped object like metal beads, and some of you have 2 different metals in your kit that you will determine the density of. You have a 10 milliliter graduate cylinder, and so you can measure the density by displacement here, right? So the amount of, well, it's more here, right? The change in volume of this is equal to the volume of the object that you submerged. Okay, what do you do if something floats? Well, you could, for example, use another liquid. Isopropyl alcohol is less dense than water, and oils are less dense. All of these organic liquids are less dense than water, and you should be able to use them. Okay, so let's just practice a couple. Right, a piece of metal has a mass of 47.6 grams and a volume of 17.6 cubic centimeter. What is the density? You just plug that in. You're given mass and you're given volume, and so the density of this piece of metal would be the ratio of 47.6 grams divided by 17.6 centimeters cubed, which is 2.70 grams per cubic centimeters. And usually, even if the metal or the solid is irregularly shaped, if it's a solid, we report the units in cubic centimeter. If it's a liquid, we report it in milliliters. Here's another example. A liquid has a density of 1.20 grams per cubic centimeter and a mass of 24.5 grams. What is the volume? Well, now I have to solve this formula for volume. So you multiply by V and you divide by D. So that means the volume is going to be equal to mass divided by density. And if you're pretty weak in algebra, then you should pay attention to your units, because if I do this now, you take the mass, which is 24.5 grams, and you divide it by 1.20 grams per cubic centimeter. The gram cancels, this appears on top, and our units are what they should be, cubic centimeters, and this is 20.4 centimeters cubed. Lead has a density of 11.3 grams per cubic centimeter. What is the mass of a piece of lead that has a volume of 250 milliliters? Okay, so now this time what we have to do, we take density equals mass over volume, and I am asking for mass, so all you have to do is multiply by V. So the mass is going to be equal to 11.3 grams per cubic centimeter times 250, and this is the same as a cubic centimeter, right? So I can change that unit so that it cancels, and my answer will be 2,800 100 grams. Okay, so that's enough of density. Let's take a look at one last measure of, well, something that we measure, energy. Okay, energy in its units. Okay, so as I said, chemistry is the study of matter, and matter undergoes changes, right? Sometimes they're physical changes. If you're melting butter or ice is melting, or if you're setting something on fire, that's a chemical change, right? So we have actually, in both of those examples, we have an energy transfer, right? And so by definition, energy is the capacity to do work. And work is what this guy is doing here. He is applying a force to an object, right? Either to pull or push an object, right? And so, and when it goes distance, then you are doing work, right? So he's applying a force, pushing it. So I guess that concept is pretty straightforward. And we measure this either in calories or in joules. Those are the units for energy. Energy can be either potential or kinetic. And so the potential energy is the energy of an object either internally stored in the bonds or by its distance to the ground, okay? And that's because this object here that's resting on a roof, there's a force, gravity, that's pulling on that, and so it has the potential to fall, and as it falls, it turns into kinetic energy, which is the energy of motion, okay? So you have, and I don't want to go into any great detail here, we have 2 more chapters that are devoted to thermochemistry. I just want to introduce the concept here, and of course the unit is more important, joules and calories. How do we measure energy? And so it turns out that that energy can neither be created nor destroyed. That's the first law of thermodynamics here. You can only transfer it from one form to another, right? But it never really goes away. So you have this object on the house up there. It has potential energy. Gravity pulls on it, falls off the roof, turns into kinetic energy. And when that object hits the ground, that energy, everything vibrates, right? So some thermal energy is going to be created there, right? So you are going to heat the floor. You're transferring this kinetic energy to thermal energy, which is energy of heat, right? And then of course it goes away to the surroundings. And you can also have gasoline, for example, has high potential energy, not because it's far away from the ground, but because its bonds are very unstable, right? And so you can actually, you know very well that you can set gasoline on fire and it'll burn, and we use that in a car to do work, to move the car forward, and we use it not very efficiently, but we can use it. And so that's also another form of potential energy. And so then the resulting products from that chemical reaction, they have lower energy. So things have the tendency to go from higher energy to lower energy, okay? And so of course we are interested only in our system, and like the car is the system, and then when we drive it, energy is the engine heats up, right? The chemical combustion gives off heat. Not all of that energy is used to move the car forward. Some of it is lost to the surroundings, and we can feel that, but at some point it just goes into the universe and the surroundings, and we can no longer feel that. But the first law of thermodynamics says that this energy never goes away, that it's always the energy of the system, and the surroundings stays the same. Okay, and so we have 2 different energetic processes that are important for chemistry especially. We have endothermic and exothermic reactions, right? So if you stick energy from the surrounding into a system, right, it picks up energy, it increases the amount of energy, right? So if you're melting something like you have water and you're heating it up. It's a simple fact of heating it up or bringing it to a boil. You're sticking energy into this, and so you are raising the temperature of that. You are sticking energy in there, and if energy is released, okay, like you're burning wood and energy is released, you can feel the heat from the surroundings. Okay, so but that also means that whatever was burning now is lower in energy. Okay, so like I said, we're going to bring these concepts back, and so now I want to pause, just go through quickly through these units, and then we only have one more lecture left where I'll practice a bunch of problems. Okay, so we have two different units that we use for energy, right? One is a calorie, and the calorie is defined by the energy required to raise the temperature of 1 gram of water or 1 milliliter of water by 1 degree. So that's defined by that. So 1 calorie is equal to 4.184 joules. That is a conversion factor, just like 254 grams equals 1 pound. And 1 joule is approximately the energy required for a heartbeat. Okay, so that's where that comes from. And we use calories are also used in food calories, but usually that's 1,000 actual calories. A food calorie is actually a kilocalorie. Okay, so when you read the food label on a box of chocolates, yeah, then that's 1,000 calories is actually a 1 calorie is actually 1,000 or 1 kilocalorie, right? Which is equal to 4,184 joules. Okay, so let's take a pause, and then when I come back, we will do dimensional analysis, right? Just